3I Atlas. 7 days left until December 19th, and everything about this object is getting harder to explain. Its path is razor precise. Its jets fire in directions no comet should manage, and its velocity jump after disappearing behind the sun still has no agreed-upon cause. Each new data point narrows the options. Either this is the most unusual interstellar comet ever recorded, or it isn't a comet at all. In this episode, we're cutting straight to the anomalies, the possibilities researchers avoid discussing publicly, and what they could mean as the countdown runs out. If clear, high signal analysis is what you're here for. Consider liking and subscribing. Let's get into it. 7 days remain before 3I Atlas reaches its closest point to Earth. In those 7 days, the picture we have built around this interstellar object is beginning to break apart. What we thought was a simple comet passing through the solar system now presents patterns that do not align with familiar behavior. The trajectory, the timing, and the 7 distinct jets that extend in directions no natural model easily explains. All of them form a sequence that is difficult to dismiss. The alignment with Jupiter, which carries a probability of less than 0.004% by random chance, pushes the discussion further. When these elements are placed together, they form a structure of events that feels intentional rather than accidental. It raises the question of whether 3I Atlas is simply moving through our region of space, or whether its approach marks the beginning of something we did not anticipate and are not prepared to interpret. The next 3 weeks stand at the center of these questions. The evidence coming together does not move toward quiet conclusions. Instead, it shifts attention toward patterns that challenge our assumptions about objects arriving from beyond our star system. There is an unease in the level of precision involved. In everyday physics, the world behaves in familiar ways. A dropped object falls. A disturbance in water spreads outward. These are predictable outcomes shaped by known forces. But when an object from another star system enters our neighborhood and begins showing timing and orientation that seem to fall into place with unusual accuracy, the mathematics becomes harder to reconcile. 3I Atlas is now less than 3 weeks from its closest approach, and the details surrounding its motion deserve careful attention. On December 19th, the object will pass at roughly 270 million kilometers from Earth. On a human scale, that distance appears safe nearly twice the separation between Earth and the Sunday. But distance alone is not the defining feature. The timing of each major stage of this object's journey through the inner solar system is where the anomalies accumulate. 3I Atlas was first identified on the 1st of July by the Atlas telescope in Chile. It entered our solar system from the direction of the galactic center, a crowded region where detecting faint, fast-moving bodies is difficult. Its path arrived at an angle only 5 degrees from the ecliptic, the thin band where the planets orbit. A random interstellar object taking on that alignment has an estimated probability of around 0.2%, 1 in 500. Then there is the matter of visibility. The object reached perihelion, its closest point to the Sun, on the 29th of October. During that critical moment, Earth was positioned on the opposite side of the Sunday. Our ground-based telescopes could not observe it. Even orbital observatories dealt with unfavorable geometry that limited viewing windows when the object would have been most active and most revealing. For weeks, it moved through a period in its orbit where essential data could not be collected. The idea of coincidence may explain a single difficult observation window, but the pattern grows when earlier passages are added. On the 3rd of October, before perihelion, 3I Atlas passed within 28 million kilometers of Mars. It then moved close enough to Venus that calculations show a trajectory passing within tens of millions of kilometers. These distances are not near misses on a cosmic scale, but they are precise alignments for a body entering from interstellar space. The sequence continues after perihelion, as the object now moves toward a future encounter with Jupiter in March of 2026, an encounter difficult to frame as random. Harvard astrophysicist R.V. Loeb evaluated the combined probabilities of the timing required for these near passages of Mars, Venus, and Jupiter while the object remained hidden from Earth at the moment of maximum solar illumination. The result was approximately 0.005%, 1 in 20,000. When improbable events multiply, the outcome becomes harder to treat as ordinary. To illustrate the pattern, imagine a museum at night. A shadow passes along the east wing precisely when a camera in that corridor goes offline. The next evening, a similar shape moves across the west wing during another brief failure. It can be dismissed once or twice, but when the pattern repeats across several nights with movements occurring only when the surveillance system is blind, the situation takes a different shape. The actions do not disrupt alarms. They avoid monitored areas. They appear to take advantage of timing that favors invisibility. At some point, coincidence loses strength as an explanation. 3I Atlas is moving in ways that appear to take advantage of observational blind spots. It does not mean intent is confirmed, but the effect resembles the behavior of something navigating with awareness of when it is visible. Mainstream scientific interpretation turns first to familiar processes. Outgassing the release of vapor as ice warms near the sun can produce acceleration, irregular jets, and complex shapes in a comet's tail. Gravity shapes the path of all objects, and orbital mechanics can produce alignments that seem improbable when viewed without context. Any one of these explanations holds weight on its own, but the behavior of 3I Atlas shows differences from typical comets. As the object came out of perihelion, data from Mars orbiters and solar observatories recorded features that do not match expectations. A comet approaching the sun should form a large tail of dust and gas flowing away from solar radiation pressure. Instead, 3I Atlas displayed at least 7 jets pointing in multiple directions. Some of them extended toward the sun, forming structures known as antitails. Antitails can form under specific geometric conditions when Earth passes through the orbital plane of a comet and dust creates an apparent reversal in orientation. But the antitails of 3I Atlas have been confirmed by multiple observatories from different positions in space. They are not artifacts of angle or illusion. They are physical jets, reaching hundreds of thousands of kilometers into space. One recorded in early November extended nearly 3 million kilometers. At typical thermal speeds of around 400 meters per second for material expelled from a natural comet, it would take roughly 1 month for particles to travel 1 million kilometers. During that time, the rotation of the nucleus, approximately 16 hours for this object, should blur the jets into diffuse spirals. Instead, the jets remain narrow and sharply defined, as if stabilized against rotational effects. On the 8th of November, images revealed a halo, nearly 500,000 kilometers wide, surrounding the nucleus, with jets holding their orientation even as the object turned. The appearance suggests continuous adjustment rather than passive ejection. This does not confirm artificial origin, but it requires accepting a chain of improbabilities if treated as a standard natural object. The mass calculations deepen the puzzle. NASA's Jet Propulsion Laboratory reported measurable non-gravitational acceleration during perihelion, meaning there was additional force acting on the object beyond gravity. For a comet, such acceleration would arise from outgassing, but to match the observed acceleration, the amount of material that would need to be expelled approaches more than 10% of the object's total mass, possibly around 50 billion tons. The estimated minimum mass of 3I Atlas is roughly 33 billion tons. The required outgassing would exceed the mass of the object itself. No debris cloud of that magnitude has been observed. Instead, the object remains compact, active, but not in the collapsing state expected from such dramatic mass loss. NASA maintains that 3I Atlas resembles a comet, pointing to its coma, its carbon dioxide emissions, and its overall shape. These observations are accurate, but resemblance alone does not resolve the inconsistencies. A convincing disguise does not require creating something unfamiliar. It requires creating something entirely familiar. If an engineered probe was sent into another star system to observe, gather data, or deploy equipment, its best defense would be to appear indistinguishable from a natural object. The idea is not new. Peer-reviewed work examining the characteristics of hypothetical extraterrestrial probes has noted that a comet-like exterior would be one of the most effective forms of concealment. In such a scenario, an object would not announce itself, it would approach quietly, embedded within a category we already recognize, so that it draws minimal attention. The concept aligns with discussions in the dark forest hypothesis, the idea that advanced civilizations may remain silent, concealed, and cautious because the galaxy may not be uniformly safe. In that context, a probe would not emit signals. It would not expose a technological surface. It would resemble a rock or a comet, arriving along a path that avoids easy detection. December 19th is 7 days away. In 3 weeks, 3I Atlas will reach its closest point to Earth, then continue outward toward Jupiter. The meeting that follows may become one of the defining moments in our understanding of what entered our solar system. Before we can understand what might happen at Jupiter, we have to slow down and look carefully at what has already happened near the Sunday. The meeting with Jupiter will not make sense unless we first come to terms with the 7 jets that appeared after perihelion. Their shapes, their directions, and the simple fact that they exist at all push against what we thought we understood about comet physics. And behind those jets sits a possibility that most scientists are not willing to say out loud. Those streams may not be simple exhaust from ice turning directly into gas. They may be something different, and if that is true, it changes the meaning of everything now unfolding above our heads. Before we dive into the jets themselves, it is worth sitting with an uncomfortable idea, a thought experiment that strips away the familiar image of what first contact, or even first conflict, might look like. For decades, science fiction has trained us to expect alien arrival as a clear, dramatic event. We imagine craft breaking through clouds, beams of light over cities, or radio signals that we can decode and broadcast to the world. We picture a moment of revelation, a line in time where everyone alive understands that the universe has spoken and said, "You are not alone." Films like Independence Day, Contact, and Arrival all share the same pattern. There is a before, there is an after. There is a single, unmistakable moment when everything changes. But what if that is not how it works? What if the most dangerous form of contact is the one you never recognize as contact at all? Think about how we study animals in the wild. The most effective wildlife researchers do not walk into the forest waving flags. They do not introduce themselves. They use camouflage. They mount remote cameras on trees. They sit at distances where their presence remains invisible. The animals continue living their lives, unaware they are being recorded, tracked, and analyzed. The observers gather everything they need without ever revealing who they are. Now stretch that logic across interstellar distances. Any civilization capable of sending objects between stars would have technology so far beyond ours that our entire system of telescopes, radar, and satellites might look to them the way campfires and smoke once looked to us. Simple, predictable, and easy to monitor without detection. If you wanted to study such a civilization, you would not land on their main world and introduce yourself. You would send something quiet, something that blends in, something that fits categories they already use, something that can slip through their detection systems while they congratulate themselves on identifying a natural object. You would send something that looks very much like a comet. The pattern forming around 3I Atlas suggests that what is approaching Earth is not just a strange object on an odd path. It may be a test of how carefully we observe the sky, a test of how we respond to anomalies, a test of whether we can spot a hunter when it is already inside the fence, moving calmly among the herd, wrapped in familiar shapes. December 19th is almost here. 7 days until closest approach. Each passing hour is an hour of data, an hour of monitoring, an hour in which something out there may be learning exactly what it needs to know about us. The central question may not be whether 3I Atlas is observing. The central question may be, what happens when it is finished observing? To move toward that answer, we have to look at what came into view when the object emerged from behind the sun, during the time when no observer on Earth could see what was happening. We have to look at the 7 jets that changed the discussion. When 3I Atlas came back into view in early November, astronomers across the planet turned their instruments toward it, expecting a fairly standard scene. A comet that had passed close to our star, warmed, and begun to release gas and dust in familiar patterns. They expected something that would fit comfortably into the textbook description of how icy bodies respond to solar heating. Instead, what they recorded sent a quiet shock through the scientific community, a shock that is still working its way through papers, conferences, and private conversations. On the 8th of November, a team, including Michael Yeager, Gerald Raymond, and Enrico Prosperi, collected a series of images using stacked exposures through green, red, and blue filters. The combined data revealed a structure around 3I Atlas that did not match existing comet models. At least 7 clear jets extended from the nucleus, reaching outward in several directions, like rigid spokes on a wheel. Some pointed away from the sun, which is what physics predicts. Others, however, pointed toward the sun, forming anti-tail structures that remained visible across repeated observations and from different angles. To understand why this matters, it helps to revisit the basics. As a comet approaches the sun, its frozen materials warm up and begin to sublimate, changing directly from solid into gas. This process, called outgassing, creates pressure on the surface. The outgoing material gets pushed by sunlight and the solar wind, flowing away from the sundae. The familiar result is the classic comet tail, which always points roughly away from the sun, regardless of the direction in which the comet itself is moving. The idea is simple enough that it is taught to children as an introduction to space science. The sun pushes. The tail points away. Anti-tails can appear in some situations. When Earth passes through the orbital plane of a comet, dust left along the comet's path can line up in such a way that, from our point of view, it seems to form a structure pointing back toward the sundae. But these anti-tails are illusions born of geometry. They depend on a specific viewing angle. Change the angle, and the apparent anti-tail is gone. It is a trick of perspective, not a stream of matter truly flowing into the solar wind. The anti-tails, linked to 3I Atlas, do not behave like these simple geometric artifacts. They have been seen over and over again on the 8th, 9th, 11th, 16th, and 17th of November, using different instruments and from different vantage points. Each time, the same structure appears. Jets pointing sunward that should not survive in that orientation. This is not a one-night anomaly or a single misprocessed image. It is a repeating feature that demands a physical explanation. Now consider what this implies in terms of forces. The solar wind near the object's location flows outward at speeds of around 400 kilometers per second. Any natural material expelled from a comet would be quickly swept back in that flow. To send material toward the Sun over distances approaching 1 million kilometers, as the November images indicate, requires that the jet carry enough momentum to push against this outflow. That means energy. It means thrust. It means something acting like a propulsion system rather than passive vapor drifting into space. Astrophysicist Avi Loeb has examined the numbers. For the anti-tail jets to extend as far as they do, their ram pressure, the pressure created by moving mass, must exceed that of the solar wind, out to roughly 1 million kilometers from the nucleus. Given that the solar wind is moving around 1,000 times faster than typical comet outgassing, the density of material in those jets must be on the order of 1 million times higher than the solar wind at their outer edges. When you work through the calculations, you find a mass flow of roughly 2 million kilograms per second across an area of about 1 million square kilometers. Over 1 month, that corresponds to a total mass loss of around 50 billion tons. That figure is not a small adjustment. For comparison, the minimum mass estimate for 3I Atlas, based on its earlier lack of measurable non-gravitational acceleration, is about 33 billion tons. In other words, the natural explanation asks us to accept that the object expelled more than its entire estimated mass in the weeks around perihelion. And yet, the November images show a nucleus that is still largely intact. It is bright. It is active, but it is not a shattered ruin. It does not look like a body that has lost 1.5 times its own mass. The question of where that supposed mass went is not a rhetorical trick. It is a direct challenge to the standard comet model, and so far, it has not been resolved in a satisfying way. The mainstream reaction has been to adjust the inputs. Perhaps the nucleus is larger and heavier than initially assumed. Perhaps the efficiency of outgassing is higher than expected. Perhaps unusual mixtures of ice behave in ways that differ from water or carbon dioxide. Each of these ideas can patch one part of the problem, but often at the cost of creating new problems in other places. The model grows more complex, more sensitive to assumptions that have not been independently verified. The description of a normal comet begins to sound less normal. There is another option, one that Loeb and others have raised with careful language. What if the jets are not being driven by sublimating ice at all? What if they are generated by a different mechanism entirely? Consider the characteristics of known propulsion systems. Chemical rockets, like those used to launch spacecraft from Earth, can produce exhaust speeds of 3 to 5 kilometers per second. Ion thrusters, which use electric fields to accelerate charged particles, can reach 20 to 50 kilometers per second. Both of these are far above the roughly 400 meters per second typical of natural comet outgassing. When exhaust velocity rises, the amount of mass needed to produce a given change in momentum falls sharply. The relationship scales with the square of the velocity. A tenfold increase in exhaust speed lowers the required mass by a factor of 100. If 3I Atlas were using some form of propulsion with exhaust speeds in even a modest technological range, the non-gravitational acceleration we observe could be explained with less than 1% of the mass loss required under the natural outgassing model. In that scenario, the jets could appear just as they do now, narrow, directed, and sustained, while consuming only a small fraction of the object's total mass. This does not prove that is what is happening, but it shows that the technological hypothesis actually demands fewer extreme assumptions than the natural one. That alone should cause us to pause. There is another feature of these jets that deserves attention: their orientation in the face of rotation. Observations built up in July and August indicate that 3I Atlas spins once every 16 hours. This was inferred from regular changes in brightness as different parts of its surface turned into and out of sunlight. A rotation period of 16 hours is not unusual for a comet. What is unusual is what such a spin should do to any streams of material coming off the surface. Imagine a garden sprinkler. As it turns, the water sprays out in a spiral pattern. The shape of that spiral depends on how fast the sprinkler spins and how fast the water flows. For a body rotating every 16 hours and ejecting material at around 400 meters per second, the jets should fan out into broad, fuzzy spirals over time. Material that left the surface half a day ago should be separated by almost 90 degrees from material being expelled now. Over distances of 1 million kilometers or more, the streams should smear into a haze so diffuse that individual jets become hard to pick out. The images, however, show something else. Observations from Frank Nibbling and Michael Buchner on the 9th of November reveal jets extending close to 3 million kilometers with sharp, coherent shapes. The streams hold their directions instead of curving smoothly with the object's rotation. To keep a jet aligned in a specific direction while the main body spins, you need active stabilization. You need constant, small corrections, like those used by spacecraft to maintain orientation. You need a system that keeps thrust pointed where it needs to go, no matter how the base is turning. Natural comets have no known way to do this. Spacecraft do. As more images became available, a particular quality in these structures stood out. It is difficult to define, yet hard to ignore. The jets do not simply look like random plumes of vapor. They look arranged. The anti-tail jets appear to stop at distances where the pressure from the solar wind would balance the jet's own push. The other jets extend along narrow paths that appear consistent over time. Taken together, the configuration has a symmetry and an apparent purpose that feel closer to engineered behavior than to chaotic evaporation. It is important to admit that this impression is, at some level, subjective. Human brains are skilled at finding patterns, sometimes too skilled. We see shapes in clouds and meaning in random noise. But we evolved that sensitivity because patterns often do signal real causes, including the presence of other agents. Ignoring every pattern on the grounds that it might be a false alarm is not more scientific than believing every coincidence is meaningful. The discipline lies in recognizing that when enough independent anomalies stack up, they deserve structured investigation. The coming weeks will bring more observations. 3I Atlas is nearing its closest approach to Earth, and major observatories are preparing intensive campaigns. The James Webb Space Telescope is expected to probe the jet spectra, breaking down their light into components that can reveal chemical makeup and velocity profiles. Large ground-based telescopes will watch changes in shape day by day. By the end of December, we will likely know more about this object than we have known in all the months since its discovery. Yet there is a troubling timing problem. By the time firm conclusions can be drawn about the nature of the jets, 3I Atlas will already be leaving the inner solar system on its path toward Jupiter. It will carry whatever secrets it holds outward, into regions where detailed observation becomes more difficult. If the jets do turn out to be technological, if they are part of a propulsion or deployment system, then we will have watched the system operate directly in front of us and responded only by recording and analyzing the period in which any real action might be considered, if action is even possible, is closing. 7 days remain until closest approach to Earth. After that, the object moves outward toward the gas giant, toward a rendezvous in March that could become the most important astronomical event of our time. What 3I Atlas does in the environment of Jupiter could tell us whether we are dealing with a passive observer or with something more active, something that came not only to watch, but to act, to release instruments, to place technology into orbits and regions we do not routinely monitor and may not detect until much later, if at all. The 7 jets have already changed the discussion because they show that this object is not behaving as a comet should. Jupiter will not just add another data point. Jupiter will reveal what 3I Atlas truly is, and the numerical alignments surrounding that encounter are so precise, so unlikely by chance, that when they were first calculated, they had to be checked repeatedly before they were believed. The coincidence waiting at Jupiter is not simply rare. It approaches the edge of what is possible without intent, as if the rendezvous and everything it may bring were written into the plan from the very beginning. A Jupiter encounter that could, in effect, seed the solar system. In all of science, there are moments when coincidence becomes so unlikely that it demands an answer. Moments when numbers line up with such sharp precision that randomness no longer feels like a sufficient explanation. What comes next is one of those moments. It is a mathematical alignment so unusual that even cautious, skeptical astronomers have had to stop and consider scenarios they would normally dismiss without hesitation. On March 16th, 2026, 3I Atlas will reach its closest approach to Jupiter. This point, called Peryov, marks the minimum distance between this interstellar object and the largest planet in our solar system. Using trajectory solutions from NASA's Jet Propulsion Laboratory, built from measurements gathered by more than 230 observatories around the world, and corrected for the non-gravitational acceleration seen near perihelion, that closest distance has been calculated with remarkable accuracy. The result is 53.445 million kilometers, with an uncertainty of plus or minus 0.06 million kilometers. Now we have to bring in another concept: Jupiter's Hill radius. In orbital mechanics, the Hill radius defines the region around a planet where its gravity dominates over the tidal pull of the Sunday. Inside this boundary, an object can remain bound to the planet in a stable orbit. Outside it, the sun's influence takes over, and long-term capture becomes much more difficult. The Hill radius is found using a straightforward formula involving the mass of the planet, the mass of the sun, and the distance between them. On March 16th, 2026, Jupiter's Hill radius will be 53.502 million kilometers. Set the two numbers side by side. The closest approach distance for 3I Atlas is 53.445 million kilometers. The Hill radius at that time is 53.502 million kilometers. The difference between them is 0.057 million kilometers, or about 57,000 kilometers. That gap lies within the stated uncertainty of about 60,000 kilometers. In other words, the current best fit trajectory brings 3I Atlas to Jupiter's gravitational doorstep. with a match to the Hill boundary at the level of roughly 1 part in 1,000. Measured across the full diameter of Jupiter's orbit around the Sun, that precision corresponds to roughly 1 part in 26,000. Under conservative assumptions about the many possible paths interstellar objects can follow, Avi Loeb has estimated the probability of such an encounter happening by chance at less than 0.004%, about 1 in 25,000. An object from another star system arrives, shows non-gravitational acceleration near our Sun, and then follows a path that takes it not simply near Jupiter, but to the exact edge of the planet's gravitational sphere of influence. Not well inside, where capture would be messy and energetically expensive. Not far outside, where it would simply pass by. It goes to the boundary itself, the narrow zone where it is easiest to insert objects into stable orbits with minimal additional energy. That is not where random comets usually end up. That is where you would aim if your goal were to leave something behind. The Hill radius boundary holds special meaning in astronautics. At roughly that distance along the line connecting Jupiter and the Sun lie 2 important locations, the Lagrange points L1 and L2. These are positions where the combined gravitational pull of Jupiter and the Sun, together with orbital motion, create pockets of relative stability. Objects placed at Lagrange points require very little fuel to maintain their positions. They can stay there for very long periods with only small occasional corrections. Our own spacefaring civilization uses Lagrange points for exactly this reason. The James Webb Space Telescope operates near the Sun-Earth L2 point. Several solar observatories sit near the L1 point between Earth and the Sunday. These locations are natural parking spots carved by celestial mechanics, ideal for instruments that need to remain in a fixed relationship to larger bodies. If 3I Atlas is simply a natural comet, its arrival at Jupiter's Hill radius is an extremely unlikely coincidence. But if 3I Atlas has some form of guidance or embedded programming, if agency is involved at any level, then the Hill sphere is exactly where you would want to be for one particular purpose: deployment. The scenario Loeb outlines follows a cold, straightforward logic. Imagine that 3I Atlas is a kind of carrier, a mothership, using comet-like features as camouflage to cross interstellar distances and slip into target star systems unnoticed. Its role would not be to land anywhere itself, but to release smaller devices, observation stations, communication relays, or systems we lack the language to describe. Where would such a carrier place these devices? Not near the inner planets, where detection risk is highest and orbital environments are crowded and complex. Not in the far outer reaches, where long communication delays and weak illumination reduce usefulness. Jupiter offers the ideal balance: massive enough to anchor stable orbits, far enough from Earth to limit easy detection, yet central enough to oversee much of the inner solar system. Within that framework, the Hill radius becomes the natural deployment zone. Release satellites slightly inside this boundary, and they can remain in Jupiter's grasp for long periods. Place them near the Lagrange points, and they can sit quietly with minimal effort, watching, listening, relaying. Drop them outside the Hill sphere, and over time the Sun will pull them away. Put them too deep inside without careful planning, and you may need more complex maneuvers to settle them into desired orbits. Right at the edge, with access to L1 and L2, is ideal. In this context, the non-gravitational acceleration that 3I Atlas displayed near perihelion gains a new layer of meaning. If we model the object's path without that extra push, we find a slightly different course that misses this precise Hill radius alignment. The additional acceleration nudged the trajectory from an ordinary distant flyby into this tightly tuned encounter. It functioned like a course correction, a small but decisive adjustment that transformed a routine passage into a carefully placed approach. It is important to state this clearly. No one can claim with certainty that 3I Atlas is an alien carrier preparing to seed Jovian space with artificial devices. But it is also true that if it were such a vehicle, this is almost exactly the trajectory we would expect it to follow. The mathematics, the timing, and the level of precision all line up with that expectation. That alignment is what makes the situation so difficult to dismiss. There is another problem layered on top of the probabilities: our inability to see clearly what will happen when the object reaches Jupiter in March. The distances are simply too vast. From Earth, even our largest telescopes will record 3I Atlas as a faint point at that range. We do have a spacecraft in the Jovian system, NASA's Juno mission, but Juno was never designed to spot small objects separating from a passing body at high altitude. Its instruments are tuned to study Jupiter's atmosphere, magnetosphere, and interior structure, not to conduct a wide search for tiny new satellites. The European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, is on its way but will not arrive until the early 2030s. By the time it reaches the system, any devices released by 3I Atlas, if such devices exist, could already be in well-established orbits, in dormant states, or positioned in regions we have no habit of examining. We might be watching the most important deployment in the history of astronomy, and yet we lack the tools to observe it in detail. This is the harsh intersection of cosmic distance and the present limits of our technology. We see just enough to suspect, not enough to confirm. Speculating about the nature of any hypothetical devices moves us into a space where imagination has to fill the gaps left by data. They could be simple, passive observers, content to watch and record for decades or centuries. They could act as communication relays, nodes in a network that does not use frequencies we routinely monitor. They might be manufacturing platforms, using material from Jupiter's surroundings to build more units in a slow, steady process. Or, in less comforting scenarios, they could be dormant weapons, waiting for a trigger we do not know how to recognize. To be honest about the situation is to admit that we do not know which of these, if any, is true. The same precision that enables careful observation can also enable careful positioning for more aggressive purposes. The same camouflage that hides arrival can hide deployment. Over the next several months, as 3I Atlas moves away from Earth and toward Jupiter, we will gather more fragments of information. The object will grow dimmer, but small changes in brightness or motion could still reveal significant releases of material. Any sudden mass shedding or large-scale maneuver might show up as a shift in its light curve or a deviation from the expected path. Juno's team will be made aware of the timing and may devote some attention to monitoring the broader environment, watching for anything unusual in Jupiter's outer neighborhood. Even so, it is likely that our view will remain incomplete. In the end, 3I Atlas will cross Jupiter's Hill radius, carry out whatever processes its nature requires or its programming dictates, and then continue outward on a path back into interstellar space. We will be left to decide whether we witnessed a remarkable coincidence or an intentional act carried out with careful foresight. The evidence will be suggestive but not decisive, and that ambiguity may persist for a long time. There is still one more part of this pattern that deserves close attention: the question of timing. Why now? Why the years 2025 and 2026? Theoretical models suggest that interstellar objects move through the inner solar system constantly. At almost any given time, there may be at least one within the orbit of Saturn. Most are never detected. They are small, dark, and move against a background of countless stars in the Milky Way's disk. 3I Atlas stands out because of its size, its brightness, and the geometry of its path. But if it is artificial, its arrival in this specific era might not be accidental at all. We are living through a narrow window in our development as a technological species. Our ability to detect faint moving objects has improved quickly in just the last few decades. The Atlas telescope network that discovered 3I Atlas only became fully operational recently. The Vera Rubin Observatory, which will dramatically increase our sensitivity to small, fast objects crossing the sky, is just beginning its work. A civilization observing us from afar, watching our progress and waiting for us to reach a certain threshold, might choose this period intentionally. Not so early that we would miss the visitor entirely, not so late that we might be able to respond in a coordinated, powerful way. Instead, they could choose a moment right at the edge, when we can see enough to notice that something unusual is happening, but not enough to change the outcome. If that is the case, then 3I Atlas is not only a physical object, but also a kind of message, or perhaps a test. It might even be an invitation, although to what and on whose terms remains deeply unclear. The Jupiter rendezvous is drawing near. In less than 4 months, one of the most mathematically improbable encounters in the history of observational astronomy will occur near the largest gravity well in our planetary system. Whatever happens there will unfold beyond our ability to watch in detail, beyond our ability to influence, beyond our ability to do anything except interpret the traces left behind. But before Jupiter, there is December 19th. Before the far encounter, there is the closest passage to Earth. And before we can fully grasp what may be waiting at Jupiter, we must understand what 3I Atlas did during the weeks when it was hidden behind the sun, carrying out changes in the one region of space where no human instrument could follow: the hidden perihelion maneuver. The hidden perihelion maneuver raises another idea, one that comes from military strategy rather than astronomy. It is called a blind spot attack. You do not strike where your opponent is looking. You do not move when they expect motion. You wait until attention is elsewhere, until sensors are limited, until geometry itself creates a natural shadow. Then, during that narrow window, you act quickly and decisively before the view clears again. 3I Atlas reached perihelion on October 29th, 2025. Its closest approach to the Sun occurred at a distance of about 203 million kilometers, just inside the orbit of Mars. That was the moment of maximum solar heating, maximum physical stress, and maximum scientific interest. And it took place when Earth was almost exactly on the far side of the Sunday. From our vantage point, 3I Atlas was in solar conjunction. The sun's glare washed out the region of sky where the object was passing. Ground-based telescopes could not see it at all. Even space telescopes had only narrow, awkward viewing windows, limited by safety constraints and orbital geometry. For several weeks, during the most critical phase of its journey, this interstellar visitor operated in practical darkness as far as humanity was concerned, shielded from our instruments by the very star that makes observation possible. You can say this was coincidence, a simple outcome of orbital mechanics, a cold alignment of celestial motions. Or you can note how perfectly it matches the conditions you would choose if you wanted to maneuver without being watched. The timeline matters. 3I Atlas was discovered on July 1st. Through July, August, and September, it was visible from Earth, and hundreds of observatories followed its motion. During that period, close analysis showed something odd. As the object moved inward and warmed, it showed very little non-gravitational acceleration. For a comet that should be venting gas as it heats, this is surprising. Outgassing normally produces a gentle thrust that pushes the body off a purely gravitational path. That deviation is often measurable. Because the deviation was small, astronomers could put a lower limit on the object's mass. If 3I Atlas were a light, fragile comet, even modest outgassing would have changed its orbit in a visible way. The observed stability meant either the activity was extremely low or the object was quite massive. Calculations pointed to a minimum mass around 33 billion tons, corresponding to a nucleus at least about 5 kilometers across. Then October arrived. As 3I Atlas drew closer to perihelion and slid behind the Sun from Earth's point of view, our ground-based tracking stopped. But Mars was in a better position. NASA's Mars Reconnaissance Orbiter, ESA's Mars Express, and the ExoMars Trace Gas Orbiter all managed to capture images during this key interval. Those datasets were valuable but limited. The spacecraft were far away. Their cameras were not built to study small interstellar bodies in detail, and the resolutions they achieved were modest. What they showed fits the basic expectations. As 3I Atlas neared the Sun, it brightened significantly. More sunlight led to more heating, more sublimation, and therefore a brighter coma. That is classic comet behavior. What they could not reveal was fine structure. From Mars' orbit, the object was still a bright blur, not a resolved nucleus with visible jets. No one on or near Earth saw detailed changes in shape or any discrete event near the surface during that time. When 3I Atlas emerged from conjunction in early November and Earth-based telescopes could look again, the situation was no longer simple. The 7 jets were there. The complex anti-tail structures were there. The tightly collimated streams reaching millions of kilometers into space were there. The non-gravitational acceleration was now unmistakable in updated orbital fits. Whatever occurred during those hidden weeks transformed 3I Atlas from an unusual but manageable comet into something that no longer fits comfortably within existing categories. We understand the general physics of perihelion passages. Strong solar heating causes volatile materials to sublimate, releasing gas and dust that form the coma and tail. Surface regions can switch on and off as their volatile content changes. Comets sometimes fragment, brighten suddenly, or sprout new jets as different parts of the nucleus respond to thermal stress. All of this is natural and well documented. But none of these standard behaviors, on their own, explain what we now see with 3I Atlas. The non-gravitational acceleration is especially troublesome. NASA's Jet Propulsion Laboratory has been revising its trajectory models as new astrometric data arrive. In late October, the radial component of the extra acceleration was estimated at roughly 1.6 times 10 to the power of -6 astronomical units per day squared. By late November, alternative models, using different assumptions about how outgassing might depend on distance from the Sun, produced values around 6 times smaller. The differences between models highlight our uncertainty. The underlying physical process is not pinned down. We are trying to make a comet outgassing model fit an acceleration profile that does not sit comfortably within that framework. Avi Loeb has emphasized that the size of the acceleration implies a significant mass loss if it is caused by normal outgassing. Thrust must be balanced by expelled momentum. For a comet to change its motion, it has to throw material in the opposite direction. The larger the change, the more mass has to be expelled. Yet the post-perihelion images show a nucleus that looks reasonably intact. It does not look like a cloud of fragments from a body that has ejected a large part of itself into space. We do not see the huge, diffuse debris field that should be present if the required amount of mass had been lost. Instead, we see a compact source surrounded by those unusual jets. This is why an alternative enters the conversation: propulsion that does not rely on low-speed cometary gas flows. Technological thrusters can achieve much higher exhaust velocities, which drastically reduces the mass needed for a given change in momentum. An object with such thrusters could perform the observed maneuvers and still retain most of its mass. And if you had that capability, perihelion would be the optimal place to use it. In astrodynamics, there is a technique called the Opeth maneuver. It uses a counterintuitive feature of orbital motion. When you apply thrust at the lowest point in your orbit, where you are moving fastest in a deep gravity well, the same amount of fuel produces a larger change in your overall orbital energy than it would farther out, where you are moving more slowly. Space missions take advantage of this effect. A spacecraft swings close to a planet, fires its engines near closest approach, and amplifies the impact of its propulsion. 3I Atlas reached its closest point to the Sun during the only period when Earth could not watch it directly. If it needed to make a major adjustment to its path, if it needed to fine-tune its trajectory to hit that narrow window near Jupiter's Hill radius, the perihelion passage was the perfect time. The Oberth effect would maximize the efficiency of any burn. The solar conjunction would minimize the chance that anyone would notice. A reverse Oberth maneuver, using the Sun's gravity to help slow down rather than speed up, would be a very effective way for an interstellar craft to shed energy and settle into a bound orbit within a new system. Doing that would require engines, propellant, and careful timing. It would also benefit from being carried out in a region hidden from the main observing planet's line of sight. We should be honest about the limits of what we know. We do not have direct proof that 3I Atlas executed deliberate thrust during perihelion. We have an orbit that shows non-gravitational acceleration. We have images taken after the event that show unexpected structures. We have the mathematical result that the resulting track now leads to Jupiter's Hill radius with extremely high precision. What we do not have are resolved images of plumes at the moment of action or spectral fingerprints of exotic exhaust. The engine firing remains an inference, not an observed fact. But the absence of direct evidence is not, by itself, proof that nothing happened, especially when the missing information corresponds exactly to a time and place where observation was extremely difficult. If you were designing a flight plan to hide your most sensitive maneuvers, this is the sort of geometry you would choose. Approach from the direction of the galactic center, where the background is crowded and early detection is hard. Arrange your perihelion to coincide with solar conjunction from the perspective of the main inhabited planet. Carry out your burns behind the sun's glare. Reappear on a new course that can still be modeled as a comet that has simply become more active near the Sunday. The SOHO spacecraft, the Solar and Heliospheric Observatory run by NASA and ESA, did see 3I Atlas during this period. SOHO uses a coronagraph to block the sun's bright disk, revealing the surrounding corona and any objects that move through its field of view. In late October, 3I Atlas crossed that field. The images show a bright point moving against a backdrop of stars. They confirm that the object survived perihelion intact, which is not guaranteed for bodies passing that close to the Sunday. But the resolution is far too low to reveal any detailed structure. We see light, not the shape of a nucleus, not the form of jets, not any localized features. The Mars-based observations help fill some gaps. They confirm that activity increased. They trace brightness changes. They place the object within a broad morphological category, yet they still fall short of revealing what was happening on scales of kilometers or tens of kilometers near the surface. The result is that what went into the hidden phase and what came out do not match cleanly. Something changed during that interval. We can measure the consequences, but we did not see the process. For scientists, this is an uncomfortable place to be. The normal instinct is to look for more data, refine models, and reduce uncertainties. But here, the most informative moment is already behind us, locked in a region we could not observe at the necessary resolution. What actually took place around perihelion might have been nothing more than complex natural evolution, thermal cracking, new vents opening, unexpected patterns of outgassing, or it might have been the main burn sequence of a mission planned with great care the moment an interstellar craft reshaped its orbit for final operations in our system. We do not know which description is closer to the truth, and we may never know with certainty. 3I Atlas is now following its post-perihelion path. It is moving outward through the inner solar system, coming to its closest distance from Earth, then continuing on its way to Jupiter. Yet the question of what happened during those hidden weeks still matters. If the object did carry out deliberate maneuvers, if it did use the sun's gravity to amplify a controlled change in velocity, then we are not dealing with a passive chunk of ice and rock drifting along a predetermined path. We are dealing with something that can act, something that can choose, something that may be following a plan. That brings us to a larger and more difficult issue. If that is the case, what do we actually do about it? What kind of response is even possible? What procedures exist for a situation that most governments have long insisted will never occur? The answer might surprise you, and it might unsettle you. First contact protocols and the silence of governments. When people hear the phrase, first contact protocols, they imagine that somewhere a detailed playbook already exists. The truth is far thinner. In 1989, the International Academy of Astronautics drafted a document called The Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence. The title sounds strong and official, as if it were a binding plan for what humanity will do if we discover that we are not alone. In reality, it is nothing of the sort. The declaration is not law. It carries no enforcement power. It offers general suggestions. Confirm any detection before announcing it, inform relevant international organizations, and do not send a reply without broad international consultation. These are polite guidelines, not operational orders. They assume a calm scientific discovery in a controlled setting, not an anomalous object tearing through the solar system with properties that do not fit any simple category. No government has a publicly acknowledged, detailed response plan for actual contact with non-human intelligence. No military doctrine is published that explains how forces would respond to an active extraterrestrial presence. No international body has clear authority to coordinate a global reaction. There have been decades of papers, conferences, philosophical debates, and science fiction stories. Yet when it comes to real chains of command, concrete contingency plans, and specific decision paths, there is almost nothing on the record. Seen against that background, the quiet, almost casual way 3I Atlas has been handled takes on a different weight. When it was first discovered in July, agencies like NASA described it in cool, measured terms. A third known interstellar visitor. Interesting to scientists. No danger to Earth. The language was steady, professional, and almost aggressively ordinary, as if to signal that this was just another comet, only one that started from very far away. When Avi Loeb and his colleagues released a paper exploring the possibility that 3I Atlas might have an artificial or technological component, the mainstream reaction was swift and skeptical. Extraordinary claims require extraordinary evidence. We have seen strange comets before. There is no need, they said, to invoke intelligent origin when natural explanations are still available. On the surface, this posture is appropriate. Science is built to resist hasty leaps to extraordinary conclusions. But beneath the reasoning, there is a tone worth noticing, a strong desire to shut the conversation down, a sense that even asking whether an object might be artificial is somehow improper. When a major celebrity asked NASA on social media whether 3I Atlas might be an alien craft, the acting administrator answered with light humor and firm dismissal. No aliens, no threat, nothing to worry about. The question hangs in the air. Based on what solid evidence could anyone state that so confidently, so early? At that stage, the object was still millions of kilometers away. Observations were partial. The perihelion passage had not even occurred. This does not require a conspiracy to explain. It points to something more basic. Institutions that are not able or not willing to face certain possibilities. Governments and scientific bodies are shaped to manage familiar categories of events. They have boxes into which things are supposed to fit. When an object arrives that does not fit cleanly, the instinct is to force it into the nearest box. Interstellar object becomes comet. Anomalous acceleration becomes unusual outgassing. Highly improbable alignments become coincidences. Admitting that we may be dealing with something without precedent would force those institutions into territory where they have no tested procedures and no ready answers. It would create obligations they do not know how to meet, so they avoid that step. They maintain a narrative of normality while the anomalies accumulate. They choose reassurance over full disclosure. At the same time, it would be naive to imagine that only civilian telescopes are watching. The United States and other major powers maintain space surveillance capabilities that go far beyond what has been described in open literature. The United States Space Force, built out of former Air Force space commands, operates sensor networks designed to track objects in Earth orbit and beyond. These systems were shaped to monitor satellites and debris, but they inevitably collect data on deep space objects as well. There are classified sensors on the ground, at sea, in the air, and in orbit. There are analysis tools the public never hears about. It would be surprising if such assets were not directed at 3I Atlas. The real question is not whether governments are paying attention. It is what they may have learned that has not been shared. Some public actions hint at deeper concern. The International Asteroid Warning Network announced a dedicated astrometric campaign for 3I Atlas from late November through late January. This is the same network that receives and distributes warnings about potentially hazardous asteroids, such as an object designated 2024 YR4 earlier in the year. Why devote resources normally used for impact monitoring to an object that everyone insists poses no collision risk? The stated reason is the scientific value of refining the orbit of a rare interstellar visitor. That explanation is plausible. Yet it is also true that intensive, coordinated tracking is usually reserved for cases that matter. Add to this the timing of a short government shutdown in the United States that affected NASA in early October, precisely as 3I Atlas was closing in on perihelion. Officially, the shutdown was driven by ordinary budget disputes with no connection to any celestial event. That is almost certainly correct. But the practical effect was reduced operations and communication from NASA during the period when the object was moving into its most hidden and most active phase. The pattern that emerges is not proof of anything. It is, however, a pattern in which transparency drops at the moments when clarity would be most valuable. It is worth asking what real preparation for an extraterrestrial scenario would even look like. The United States Air Force maintains units known as Space Aggressor Squadrons, the 26th and 527th, based in Colorado. Their job is to simulate adversary threats to American and Allied space assets, to develop tactics and strategies for protecting satellites and other orbital infrastructure. Officially, their focus is on rival nations such as China and Russia, which already have demonstrated anti-satellite capabilities. In principle, though, the skill set and tools they use could be extended to other kinds of threats in space. There is also a wider web of multinational cooperation on space security, joint exercises, and shared tracking data. These efforts are framed entirely in terms of human adversaries. Whether anyone in those circles has ever seriously planned for contact with a non-human intelligence is not something we can see from the outside. History shows that governments have at least thought about the social impact of discovering life elsewhere. In 1960, the Brookings Institution produced a report for NASA called Proposed Studies on the Implications of Peaceful Space Activities for Human Affairs. Part of that document considered what might happen if evidence of extraterrestrial life were found. It suggested that such a discovery could be deeply disruptive, particularly for some religious communities and for societies with strong beliefs about human uniqueness. Some people have later claimed that the report urged permanent suppression of any such evidence. That is an exaggeration. The text is more cautious than that. It recommends studying how different groups might react and considering how to manage information carefully. But the report makes one thing clear. Questions about how to handle a discovery like this have been on the table for more than half a century. The public has not been told what conclusions, if any, were drawn. More recently, the United States Department of Defense created the All-Domain Anomaly Resolution Office, charged with examining unidentified phenomena reported by military personnel across air, sea, and space. Its founding was a reluctant recognition that some observations remain unexplained and deserve systematic study. The office is focused mainly on unidentified aerial phenomena near Earth. Whether its mandate includes objects like 3I Atlas is not specified in public documents. Still, its existence signals that at least some parts of government are willing to admit that anomalous events occur. All of this builds toward an uneasy conclusion. We have the technical ability to monitor space and to respond to threats against satellites. We have institutions that could, in principle, coordinate actions, but we lack any clear, openly shared protocol for responding to a potentially artificial object moving through the solar system. We have powerful surveillance systems, paired with very little transparency about what they see. We have officials who reassure the public, but seldom present detailed evidence to justify their confidence. The silence from governments about 3I Atlas might mean they truly know little more than we do. They may simply be watching the same telescope data, using similar models, and reaching the same uncertain conclusions. The dismissive language may reflect honest belief that this is just a strange comet, with natural explanations that will eventually become clear. Or the silence could mean that more is known than can easily be shared, that information is being weighed against fears of panic or geopolitical consequences, that decisions about disclosure are being made far from public view. From the outside, we cannot tell which picture is closer to the truth. What we can say is that blind trust in official reassurance is not justified by past behavior. The same institutions that long insisted they had no interest in unidentified aerial phenomena were later shown to have collected and analyzed such reports in secret programs. Confidence is earned through open evidence and consistent honesty. On 3I Atlas, such openness has been rare, so we are left to wonder, what will happen if the next weeks bring observations that no natural model can absorb? What if data from the closest approach to Earth show behavior that cannot plausibly be explained as outgassing or fragmentation? What if the rendezvous near Jupiter produces hints of smaller objects separating from the main body and settling into orbits near key gravitational points? What if the pattern crosses a threshold where strange comet is no longer a credible label? The uncomfortable answer is that we do not know what any official response would look like, if it exists at all. The plans, if they are written, remain behind classification barriers. The drills, if they have been run, are not acknowledged. We would be stepping into a situation for which no public map has been drawn. That is the deeper reality beneath the numbers and trajectories. We are not only dealing with an object that challenges our models of comet physics, we are also confronting a structure of governance and expertise that may not be ready for what such an object could imply. As 3I Atlas comes closer, as the calendar moves toward December 19th and then toward March, we wait for information that may or may not come from official channels. The more realistic hope may lie with independent observers, with scientists willing to risk their reputations by asking difficult questions, and with members of the public who insist on looking at the data themselves rather than accepting easy dismissal. In the end, however, the most important answers may not come in the form of press releases or policy documents. They may come from 3I Atlas itself, from what it does or does not do, from events rather than words. If there is something aboard that object with intentions that include Earth, then those intentions will eventually be expressed through action. The first moves of such an engagement would not necessarily resemble anything from popular films. There would be no dramatic fleets hanging over cities, no visible beams in the sky. Instead, we would have to think in terms of realistic capabilities and vulnerabilities, information control, infrastructure, orbits, and signals. That kind of thinking is not comfortable, but comfort is not what this moment requires. The mass ejection problem does not care what anyone prefers to believe. It is built from measurements and equations, and those do not change because a theory is convenient. People can misread or downplay the numbers, but the values themselves stay fixed. From the beginning, the numbers around 3I Atlas have been pointing at something most analysts do not want to face. This is not a small technical detail. It is a central conflict inside the natural comet explanation, so strong that fixing it means either bending basic physics or considering possibilities many scientists find uncomfortable. The logic starts before perihelion. Between July and September, tracking from hundreds of observatories showed that 3I Atlas followed an almost purely gravitational path. There was little or no measurable non-gravitational acceleration. For a warming comet with a visible coma, that is unusual. Normally, gas flowing off the surface gives the nucleus a gentle push. If that push is not seen, either the outgassing is very weak or the object is very massive. The visible activity ruled out the almost no gas option. That left mass. Estimates placed the minimum mass around 33 billion tons, corresponding to a nucleus several kilometers wide. Around perihelion, the behavior changed. Updated orbit fits from late October and November showed clear extra acceleration that gravity alone could not explain. For a natural comet, this extra push must come from outgassing. Gas is released, expands into space, and the nucleus feels a reaction force. If we know the acceleration, we can compute the required force. From that force and a typical exhaust speed, we can infer the mass flow. For normal cometary gases, the typical speed is about 400 meters per second, set by the physics of sublimation and molecular mass. It is not a knob we can turn freely. With that speed, the observed acceleration of 3I Atlas implies that it had to lose on the order of 10 to 20% of its total mass during perihelion. For a 33 billion ton object, that means roughly 3 to 7 billion tons of material. Some analyses, depending on details, suggest even higher amounts, up to values comparable to the entire estimated mass. That much material does not simply disappear. Billions of tons of gas and dust should create a large, expanding cloud, scattering sunlight, producing strong spectral signatures, and visibly diluting the nucleus. Yet post-perihelion images show a bright, active, but compact object. They show distinct jets and a well-defined coma, not a vast faint halo marking catastrophic loss. Photographs from mid-November, including those by experienced observers, present a central source that still looks intact. There is no obvious debris field of the scale the natural model demands. Several fixes have been suggested. One is that the original mass estimate is too low, and 3I Atlas is far heavier. In that case, losing several billion tons might not produce dramatic visual changes, but to make the numbers work, the nucleus would have to be much larger than current brightness and distance data support. We lack a sharp image of the solid core, so there is uncertainty, but there is no sign that we are dealing with a truly giant body far above a few kilometers in size. Another idea is that the outflow speed could be much higher than usual because of exotic ices. It is true that gases like carbon monoxide and carbon dioxide can escape more readily than water, and spectra show that carbon dioxide is present. However, these differences change speeds by factors of a few, not by factors of 10 or 100. They reduce the problem, but do not remove it. A third proposal is that the acceleration might have been produced in a short, intense burst instead of over the whole perihelion arc. A shorter thrust period would require less total mass, but a burst strong enough to alter the path of a 33 billion ton body significantly in a brief time would almost certainly produce a marked brightening or obvious outburst. No such clear event has been reported, though our coverage near perihelion was incomplete. All of these attempts modified details without resolving the core issue. The simple reading of the numbers is that a natural comet with ordinary outgassing cannot easily match both the low pre-perihelion acceleration and the strong perihelion acceleration, while remaining as intact and compact as observed afterward. At the edge of this difficulty sits another possibility, that at least part of the acceleration did not come from low-speed gas release at all. Here, known technology changes the picture. Chemical rockets send exhaust out at roughly 3 to 5 kilometers per second. Ion engines reach 20 to 50 kilometers per second. More advanced concepts could go higher. In all cases, the thrust depends on mass flow times exhaust speed. Raise the speed, and you can lower the mass needed for the same effect. A tenfold increase in exhaust speed cuts the required mass by roughly a factor of 10. An ion thruster, with speeds 50 to 100 times higher than comet gas, could in principle use 50 to 100 times less mass. If 3I Atlas were using some kind of propulsion that reached even modest technological performance, the total mass required to explain the observed acceleration would fall by 1 to 2 orders of magnitude. The missing billions of tons largely vanish from the bookkeeping. The mass ejection problem almost disappears if you allow for engines. That does not prove there are engines. it does show that technology offers a straightforward solution, while purely natural models have to stretch. The natural explanation effectively asks for a comet that loses vast amounts of mass without showing the expected debris field, or for gas speeds that do not match thermal physics. The technological explanation asks only for the existence of an intelligence somewhere else that has reached our neighborhood. Neither claim is confirmed, but only one requires us to rewrite basic physical behavior. The morphology of the jets adds another layer. In ordinary comets, jets form when local patches of volatile material heat up and vent as the nucleus rotates. These jets tend to curve and fan out, creating spiral or arc-like structures. Each jet is tied to a particular source region and is shaped by the spin. 3I Atlas shows a different pattern. Its jets appear to hold their directions despite a rotation period of about 16 hours. They extend along several fixed axes, some of them pointing roughly sunward against the solar wind. They stay narrow and coherent over distances of millions of kilometers, across timescales that should smear natural plumes into diffuse haze. To make that work with standard comet physics, you would need a very specific arrangement. Multiple active regions, located and timed so that their outputs align, emission rates that stay finely balanced, and reservoirs that act in a coordinated way across the body. It is not impossible, but demands a highly tuned configuration. An alternative is that these jets are not simple vents, but engineered outputs, thrusters, or controlled dispersal systems designed to produce particular visible effects while also managing motion. From that perspective, the strange stability of the structures is not a bug to be explained away. It is the expected signature of machines doing their work. This distinction matters. A natural comet will behave in line with known science. It will gradually quiet as it moves away from the sunday. It will follow a path set by gravity and gentle outgassing, past Jupiter and leave the solar system. A technological craft has choices. It can perform further burns. It can deploy secondary objects. Its path near Jupiter may reflect planning rather than passive response. Over the next months, several types of observations can push us one way or the other. Spectra of the jets can reveal their speed and temperature distributions. Natural sublimation has well-known patterns. Technological exhaust might show different shapes or compositions. Precision tracking of the orbit can reveal any new deviations beyond what current outgassing models predict. Any further course changes, especially if they occur when we least expect them, would be difficult to explain with simple ice turning into gas stories. At Jupiter, even course data might be enough to show whether new objects appear in key regions such as the Hill sphere or near Lagrange points. Detection will be hard, but if sizable satellites suddenly show up where none were before, that would be hard evidence of artificial activity. However this unfolds, the mass ejection problem will have to be faced. Either new data and refined models will reconcile the observed acceleration and structure with a purely natural comet, or they will keep the tension alive until the technological interpretation can no longer be brushed aside as mere speculation. What is striking now is how few outside a small circle are paying attention to this core inconsistency. The mass ejection problem is not buried in fine print. It cuts directly through the standard narrative that 3I Atlas is just a strange but natural comet. Yet the broader scientific establishment tends to glide past it, preferring gentle reassurance to hard confrontation with the numbers. That response is understandable at a human level. To admit that the numbers do not fit is to admit that something important might be missing from our picture. To accept that opens the door to the idea that we may be watching an artificial object And that idea carries social, political, and professional consequences. It is simpler to treat every anomaly as a small adjustment problem and move on. But science, at its best, is not about comfort. It is about following evidence where it leads. The acceleration data are evidence. The jet geometry is evidence. The precise match to Jupiter's Hill radius is evidence. Together they say that 3I Atlas does not yet fit a clean, natural model. The implied mass loss of tens of billions of tons per month, the still intact nucleus, the long, stable jets, the hidden perihelion changes, the carefully tuned trajectory each could, in theory, have an innocent explanation. Taken together, they form something larger than a list. They form a pattern. That pattern might be the first clear trace of what we have been searching for in radio signals and star surveys for generations. Or it might be the trace of something that has been searching for us, gadgets from the stars. Imagine, for a moment, an intelligence that operates on timescales almost beyond our imagination. Its civilization has existed not for a few centuries, but for millions of years. Perhaps even for billions. It has mapped the galaxy. It knows which stars have planets, which planets might host life, which worlds might eventually develop technology. It is patient in a way that a species with lifespans of less than a century cannot easily grasp. How would such an intelligence explore? How would it monitor? How would it spread its presence across distances that even light takes thousands of years to cross? The obvious answer is that it would not send crewed ships at all. It would send probes, autonomous systems able to operate indefinitely, to repair themselves, to make decisions based on long-term goals unfolding over eons rather than decades. And it would design those probes to be hard to notice, blending into the natural background of space, watching quietly and revealing themselves only if or when circumstances demanded. This is not fantasy. It follows directly from extending our own behavior forward in time. We have already sent probes beyond our solar system. Voyager 1 and Voyager 2 carry plaques and golden records as symbolic messages. Pioneer 10 and Pioneer 11 carried engraved panels. These vehicles are crude by any advanced standard, limited by 1970s technology, but they show the principle. We send machines ahead of us to watch, and, possibly, to be found. Now extend that idea to a civilization millions of years ahead of us. One of the most important concepts in this context was explored by mathematician John von Neumann in the 1940s. He studied self-reproducing automata machines that could, in principle, build copies of themselves using raw material from their surroundings. Applied to space, the idea is simple but powerful. A single probe could arrive in a new star system, harvest local resources, construct copies of itself, and send those copies onward. Because replication is exponential, the numbers grow quickly, even with very conservative assumptions. The result is startling. Imagine each probe takes 1,000 years to reach a new system and, once there, builds only 2 copies. After just 10 million years, a blink on galactic timescales, a single original machine could have descendants in essentially every star system in the Milky Way. The galaxy is more than 13 billion years old. There has been time for this process to run not just once, but many times. The implication is uncomfortable, but clear. If self-replicating probes are possible, and if even one civilization in the entire galaxy ever decided to deploy them, then such probes should already be here. Not arriving now for the first time, but present for a very long time, quietly occupying stable locations, monitoring without drawing attention. This deepens what is known as the Fermi paradox, the question of why we see no obvious signs of extraterrestrial intelligence, despite strong arguments that it should exist. The von Neumann probe scenario says that evidence of advanced machines ought to be common, not rare, unless those machines are built to stay hidden, unless their primary purpose is observation, not contact, unless they only step out of the shadows when particular conditions are satisfied. 3I Atlas is now on its way to Jupiter, on a path that will bring it to the very edge of the planet's Hill radius, the region where objects can remain bound to Jupiter's gravity over long periods. It is the ideal place to leave things behind. Inside that boundary, stable orbits become possible. Outside it, the sun will tend to strip objects away. If you wanted to deposit devices that would sit in the Jovian system for ages with minimal effort, you would place them near that boundary. What might those devices be? The most conservative answer is surveillance platforms, instruments designed to listen to radio and other electromagnetic emission, to watch spacecraft trajectories, to monitor planetary atmospheres and surfaces. We already use similar tools ourselves. Earth is surrounded by satellites that watch, measure, and record. A small network of probes in and around Jupiter's Hill sphere could monitor the entire inner solar system, including Earth, from a position that is difficult for our current detection systems to probe in detail. Another possibility is communication infrastructure. Real-time conversation across interstellar distances is impossible, but local relay networks can greatly improve communication within a star system and back to some larger structure. Devices parked at Jupiter, Saturn, in the asteroid belt, and farther out could function as nodes in a broad mesh, linking our system to others. If 3I Atlas is part of such a system, it might be here not only to observe, but also to plug us into a network that already exists. More speculative options go further. The deposited devices could be manufacturing platforms, self-replicating factories that use ice, rock, and metal from Jupiter's moons or the asteroid belt to build more hardware. Their production could be slow, taking centuries or millennia, and still eventually produce a large technological presence without our awareness. Or the devices could be dormant capabilities, systems designed for defense or enforcement, waiting, listening, ready to act if certain conditions are met. This ties into what is sometimes called the dark forest hypothesis, the idea that advanced civilizations may see the universe as a dangerous place and choose to eliminate potential threats before those threats become powerful. In that picture, a distributed network of probes in many star systems could serve as the mechanism that enforces such a policy, acting quietly against species that cross certain technological thresholds. The point is not to declare that this is what is happening. It is to admit that once you allow for self-replicating, long-lived probes, both peaceful and hostile roles are possible. The same technology that can serve as benign eyes and ears can also, in principle, serve as hands and weapons. From our current vantage point, we cannot tell which, if any, of these roles applies. The behavior of 3I Atlas is at least consistent with a deployment scenario, a hidden perihelion maneuver that nudged it onto a very precise Jupiter approach, the appearance of multiple jets that might, in an engineered system, correspond to final tests or separation events, and a trajectory aimed at the Hill radius where released objects could remain gravitationally secure. If something is dropped off during the Jupiter encounter, what are we likely to see? The honest answer is probably nothing. The distances are simply too large. Juno, the spacecraft currently studying Jupiter, is optimized to study the planet and its immediate environment, not to scan for small new objects in distant orbits. The European Space Agency's JUICE mission will not arrive for years. From Earth, 3I Atlas is already a faint point of light. Any devices let go near Jupiter would have to be very large to be picked up by our telescopes. Objects only a few meters or tens of meters across would vanish into the noise. Even bodies kilometers wide would be challenging to detect against Jupiter's brightness and the dark background of space. That is one of the most unsettling features of this whole picture. It is entirely possible that we are watching the delivery or reconfiguration of technology in our own solar system and do not have the tools to prove it. We may suspect but never confirm. The uncertainty itself may be deliberate from the perspective of whoever designed such a system, a layer of ambiguity that allows plausible denial, that keeps us off balance, aware enough to know that something odd is happening, but never able to pin it down fully. There is yet another interpretation worth considering. Perhaps 3I Atlas is not mainly a carrier, but a signal. Perhaps its purpose is less about what it leaves behind, and more about the fact that it came in a way we could not ignore. Think about what was required for us to notice it. We needed wide-field survey telescopes sensitive enough to spot faint, fast-moving points of light. We needed software and people able to recognize their paths as unusual. We needed global networks of observers ready to follow up. All of that infrastructure has only come together recently in human history. The Atlas survey that discovered 3I Atlas has been fully active for only a short time. The Vera Rubin Observatory, which will dramatically boost our ability to find interstellar objects, is just beginning operations. An external intelligence watching Earth might choose to wait until we reach this level, not so early that their probe would pass entirely unnoticed, but not so late that we would be able to intercept, challenge, or hide it. In that frame, the timing is not random, it is part of the design. The object itself becomes the message. If that is the case, then the anomalies we see are intentional. The near-perfect alignment with Jupiter's Hill radius, the strange jets, the mass ejection problem, these might be features placed there to force us to think, to push us to consider the existence of someone else and the scale of their capabilities. The content of the message could be as simple as, "We exist, and we can do this." Or it could be a test, a way to measure our observational power, our analytical strength, and our willingness to look beyond comforting explanations. Humans have long told stories in which powerful beings visit in disguise to judge how people behave. In those stories, the outcome depends not on whether the visitors can be resisted, but on how the visited respond, whether they act with honesty, curiosity, and care, or with denial and fear. These are myths, not equations. But sometimes myths carry rough patterns that echo real dilemmas. What seems more and more likely is that we are being watched in one way or another. Perhaps we have been watched for a long time by devices we have not recognized. Perhaps 3I Atlas is part of that watch. Or perhaps it is the first visible probe we are capable of studying. We do not yet know which. We also do not know what kind of response, if any, is expected from us. We cannot choose what 3I Atlas is. If it is simply a comet, then our task is to refine our understanding of comet physics. If it is a technological presence, then it represents an attention from outside our species that we did not invite and cannot control. In either case, what we can choose is how we respond intellectually. We can improve instruments. We can build better international systems for sharing and analyzing data. We can move away from automatic dismissal when confronted with serious anomalies. We can prepare our minds even if we cannot prepare our defenses. December 19th approaches. Then comes March and the encounter near Jupiter. After that, 3I Atlas will head outward toward deep space. Whatever it leaves in its wake around Jupiter or in our understanding will shape how we think about ourselves and our place in the galaxy for a very long time. The gadgets from the stars, if they exist, might turn out to be tools of learning or tools of control. They might signal an invitation or mark a boundary we are not meant to cross. We do not get to decide what they are. We only get to decide how seriously we take them and how honestly we face the questions they raise. That brings us back to the issue we have been circling. If 3I Atlas is not a passive comet, but an active presence with unknown aims, what can humanity actually do? What options does Earth really have when confronted by technology that has already crossed light years to get here? The answer is sobering, but it is not entirely hopeless. Earth's impossible defense. If 3I Atlas is the product of a technological civilization capable of crossing the distances between stars, and if that civilization holds hostile intent toward Earth, then we need to be honest. We have almost no defense. This is not pessimism. It is a simple consequence of physics. Any species that can send a functioning probe across light-year distances has mastered energy scales, materials, and computation far beyond anything we currently possess. The energy required to accelerate and then decelerate a substantial craft between stars is greater than the total energy output of human civilization over many years. The materials must endure constant radiation, impacts from dust and micrometeoroids, and long periods of stress without repair facilities. The navigation and control systems must operate autonomously for decades or centuries. That implies levels of artificial intelligence far above the systems we are just beginning to build. In strategic terms, this is not a small advantage. It is an asymmetric gap of a different kind. It is not like facing an opponent with slightly better ships or slightly more advanced missiles. It is like a Stone Age tribe facing a modern industrial military. The categories of conflict do not match. Our most powerful weapons, nuclear devices, release energies measured in a few tens of megatons of chemical explosive equivalent. An interstellar civilization could redirect modest asteroids that unleash thousands of times more energy without much effort. Our fastest missiles move at a few kilometers per second. Interstellar craft must routinely handle speeds of many tens of kilometers per second, and advanced propulsion could bring them to significant fractions of the speed of light. We cannot intercept what we cannot meaningfully track. We cannot track what we cannot yet understand. That is the sober baseline. Against a true interstellar attack, we have no realistic military options. But that does not automatically mean we are doomed, because the whole framing of attack and defense may be wrong. Before we imagine battles we cannot win, we should ask a quieter question. Why would a civilization with such capabilities travel so far to harm us in the first place? The obvious motives do not hold up well. Raw resources are abundant in space. Everything valuable we have in terms of water, metals, and organic molecules exists in far greater quantities in asteroid belts, icy moons, and gas-rich outer regions of countless other systems. Climbing down into Earth's deep gravity well to extract resources makes little sense for a species that can mine freely in environments without atmosphere, weather, or native ecology. Living space is not a strong motive either. Any civilization that can cross interstellar distances can almost certainly build artificial habitats, orbital stations, large rotating habitats, networks of free-flying structures. These can be tuned precisely to whatever environmental conditions they prefer. The effort required to conquer and reshape an existing biosphere into something compatible with alien life is enormous. Building tailored habitats in space would be easier. The darker idea is preemptive elimination, the stark version of the dark forest hypothesis. In that view, civilizations destroy emerging rivals as soon as they notice them, simply to remove future threats. But that logic raises a problem of its own. If the real goal were to quietly erase us, why send visible probes at all? Why approach in a way that invites detection, debate, and observation? A civilization able to manage interstellar dynamics could have launched a large rock from the outer solar system long ago, aimed with enough precision to hit Earth at high speed. Such an object would be virtually impossible for us to detect in time, and the result would be extinction without warning. No gradual approach, no three-eye atlas, no chance to even know that something had happened. The fact that we are watching this object, arguing about its nature, and talking about its path, suggests that immediate destruction is not what is happening. If the intentions are hostile, they are at least complicated. And it may be that hostile is the wrong word entirely. There is another analogy we can consider, drawn from our own behavior on Earth. When we study wild animals, we do not usually arrive with armies. We watch them from a distance. We tag them with transmitters. We alter their environment in ways they cannot comprehend. For the animal, being captured, sedated, implanted with a device, and released is a terrifying and inexplicable event. For the biologist, it is data collection. Three-Eye Atlas could be the cosmic equivalent of a tagging mission, a long-duration observation platform designed to collect information about a young technological species. From our point of view, any interference may feel threatening or incomprehensible. From the perspective of a far older intelligence, it might simply be one more field study among many. We do not know which picture is correct. We do not even know with certainty that any intelligence is involved. But these possibilities hint at something important. Even if we cannot fight in any meaningful sense, there are still responses that make sense. The first and most obvious is improved observation. Before anything else, we need to know what Three-Eye Atlas actually is doing. That means coordinated spectroscopic campaigns to measure jet composition and speed. It means continuous, high-precision tracking of its trajectory to catch any subtle course changes. It means making full use of ground-based telescopes, space observatories, and any interplanetary probes that can safely point their instruments in its direction. Some of this is already underway, but often as a side project, not as a global priority. Treating Three-Eye Atlas as a central target rather than as a curiosity would be a rational step. The second is transparency. Whatever is learned should, as much as possible, be shared. Scientific results should be published in the open. Government assessments should be reported honestly. Keeping findings behind classification walls offers little advantage in this context. If the object is natural, open data will only strengthen trust. If it is not natural, then wider awareness will allow more minds to work the problem. Hidden information breeds rumor and weakens our ability to respond intelligently. The third is communication. If someone is watching, it may be better to acknowledge that we are aware. Sending carefully constructed messages directed along Three-Eye Atlas's path would not guarantee any response. It might not even be noticed. But the act itself signals something important about us, that we recognize the possibility of others, that we choose curiosity over automatic hostility, that we are willing to engage in dialogue rather than pretend nothing unusual is happening. Arguments that we should stay silent, to remain hidden, do not carry much weight anymore. Our radio noise and atmospheric signatures have already revealed our presence to any civilization capable of launching interstellar probes. A fourth response looks beyond this single object. Whatever 3i Atlas turns out to be, it will not be the last interstellar visitor we detect. With new survey telescopes like the Vera Rubin Observatory coming online, our ability to find fast, faint objects will grow dramatically. Sooner or later, one of those objects will be so clearly artificial that denial becomes impossible. Waiting until that day to think about response frameworks would be a mistake. We should begin building international structures now for observation, communication, and decision-making, so that when that moment arrives, we are not improvising under pressure. None of this changes the immediate limits. If 3i Atlas is releasing technology into Jupiter's environment, we will not stop it. If it decided to alter course toward Earth, we could not intercept it. If it has already peppered the solar system with observation nodes, we likely cannot find them with current tools. What we can control is our own posture. Whether we face the unknown with eyes open or retreat into dismissal and denial, the universe was never obliged to be safe. It is vast, indifferent, and old. 3i Atlas reminds us of how small and young we are, and of how limited our power is beyond our own planet. Our weapons mean little against distances measured in astronomical units and times measured in millennia, but our strength has never only been about weapons. It has also been about curiosity, the ability to learn, to cooperate, and to adapt. Those qualities may not decide whether an encounter with extraterrestrial intelligence happens, but they may strongly influence what that encounter becomes for us. A crisis we stumble through blindly, or a turning point we approach with as much understanding as we can muster. The impossible defense is not a wall of missiles in space. It is a state of mind. It begins with accepting where we are weak and working hard in the areas where we can grow. Better instruments, clearer communication, wiser institutions, and a public that is not shielded from difficult truths. 3i Atlas is approaching. We cannot send it away. We cannot fully know its purpose, but we can watch, think, and learn. That, in the end, may be exactly what is being evaluated. The reconnaissance theory. There is another framework that deserves serious attention, one that stands beside the invasion scenario but does not rely on immediate conflict. It is simpler, quieter, and in many ways more unsettling. What if 3i Atlas is not the main event at all? What if what we are seeing is reconnaissance the scout, not the army, the survey, not the strike? In military doctrine, reconnaissance serves clear purposes. It gathers information about an opponent's position and capabilities. It identifies weaknesses and preferred approach routes. It watches how defenses behave when something unexpected appears. And perhaps most importantly, it sends its findings back to the main force so that larger decisions can be made with accurate intelligence. If we apply that logic to a cosmic scale, the meaning becomes difficult to ignore. 3i Atlas may not be here to act. It may be here to learn. Think about what a single pass through our solar system could reveal. With the right sensors, the object could map every major structure from Mercury to the Kuiper Belt. A probe of sufficient sophistication, even at large separation from Earth, could extract chemical details from our atmosphere, recognize the signatures of biology, detect industrial gases, measure waste heat patterns, and catalog the electromagnetic leakage we have been emitting for more than a century. It would not need to approach us closely to form a complete picture of our technological level, our environmental state, and our global distribution. We have done similar things on far smaller scales. Voyager, Pioneer, and New Horizons collected immense amounts of data during brief encounters with distant worlds. A civilization older than ours by millions of years would be able to collect far more. Just as important as the scientific data is the behavioral data. How does humanity react when something anomalous enters the system? Do we detect it quickly? Do we investigate or ignore? Do we cooperate across national lines or retreat into separate interpretations? Do we treat the anomaly with curiosity, caution, or denial? 3i Atlas has already provided answers. Our networks detected it. Our astronomers began analyzing it. Governments issued calming statements. Social media spread speculation at remarkable speed. All of this creates a detailed picture of who we are and how we respond under uncertainty. There is also the question of capability assessment. A reconnaissance mission would observe the reach of our telescopes, the precision of our orbit tracking systems, the sensitivity of our space-based sensors, and the limits of our launch infrastructure. It would see exactly what we can and cannot do. It would measure our blind spots, our observation gaps, and the degree to which we recognize patterns or dismiss them. In effect, 3i Atlas has prompted us to reveal our strengths and our shortcomings simply by its presence. If this object is operating as a scout, the implications are broad. A scout does not act alone. It gathers data for something that comes later, perhaps decades later, perhaps centuries, perhaps longer than we can reasonably imagine. It may be only one unit within a much larger collection of probes distributed across many star systems. It may have predecessors we never detected. It may have successors already on their way. The idea is not comforting. Reconnaissance is, in some ways, more difficult to face than open aggression. An attack announces itself. Reconnaissance leaves only questions. If 3i Atlas is gathering information, then it will leave without revealing its conclusions. We will be left to wonder whether its observations will influence decisions made far away, decisions about whether to approach us, avoid us, study us more deeply, or intervene in ways we cannot predict. The uncertainty stretches into the future with no clear boundary. This is not speculation without precedent. Human history contains many examples, even if they are imperfect analogies. When technologically advanced societies first encountered isolated cultures, the pattern often began with distant observation, cautious approaches, and careful assessments. Only later came decisive actions, informed by what the initial surveys revealed. The societies being observed rarely understood the nature of those first contacts. They did not realize they were being evaluated. By the time they did, their future had already shifted. We may be in a similar position now. 3i Atlas might not be the first probe to enter our system. It may simply be the first one we noticed. Our detection capabilities have increased dramatically only in recent years. Interstellar visitors too small or too faint to observe may have passed by before. The lack of earlier detection tells us nothing about whether earlier reconnaissance occurred. This leads to anthropic reasoning as one of the few tools we can apply. If we imagine ourselves as the advanced civilization, what would we do? We would observe emerging technological species from a distance. We would send small, unobtrusive probes. We would minimize interference and gather data systematically. We would not reveal ourselves unless a specific threshold was met. If that is what we would do, then it is plausible that others, far older and more capable, would behave similarly. The reconnaissance theory does not claim certainty. It does not say that contact, partnership, or conflict is guaranteed. It simply offers a structure for interpreting what we see, a preliminary stage in a longer process. If true, then 3i Atlas is not the message. It is the survey. Its purpose is not to act, but to inform later decisions. And that is where the discomfort lies. If it is a survey, Then something receives the report, something interprets it, and something decides what happens next. 3I Atlas will soon depart toward Jupiter and then toward interstellar space. It will leave behind no clear answers, only the weight of possibility. The question is no longer only what the object is, but what purpose its passage serves, and whether this is the end of the story or merely the end of Phase 1. The countdown continues. 7 days to closest approach, then the long recession toward the outer system, and behind the fading point of light, the unresolved question that now sits within us. What happens after the scout reports home? If the reconnaissance theory is even partly correct, then whatever comes next depends on what was learned. We can only hope that, from the perspective of whoever or whatever sent 3I Atlas, there is something about us worth preserving or engaging with. The alternative possibilities are not comforting. The countdown to December 19th continues. 7 days. In 7 days, 3I Atlas will reach its closest point to Earth, about 270 million kilometers away, roughly 1.8 astronomical units. That is the nearest this interstellar visitor will ever come to the world that has been watching it with a mixture of fascination and unease. After that, it turns its attention outward, toward Jupiter, toward the cold outer system, and eventually back into the space between stars. The window is closing. Whatever 3I Atlas is, whatever it may mean, the time in which we can study it at its best is limited. This is not a thought experiment. It is not a classroom exercise about hypothetical comets. It is a real object moving through our sky, on a schedule dictated by orbital dynamics, not by human readiness. The next few weeks are our best chance to collect data that might break the stalemate between competing interpretations. As it approaches closest approach, its apparent size grows, its brightness peaks, and its structures, if they are there, become easier to resolve. Major observatories will lock on as conditions allow. Space telescopes such as Hubble and James Webb can, in principle, contribute high-precision measurements. Ground-based facilities across the world will track its path night after night, as long as it remains well-placed in the constellation Virgo. The question that hangs over all of this is simple. What will we see? Will the multiple jets remain as they have been? Or will new features appear? Will the orbit track exactly along the predicted curve? Or will additional non-gravitational accelerations show up as subtle deviations? Will detailed spectra of the coma and jets reveal chemistry consistent with ordinary ices? Or will we find hints of something that does not quite fit? The observations will come. The analyses will follow. By the end of this intensive period, we will almost certainly know more than we do now. But more is not the same thing as enough. Up to this point, 3I Atlas has specialized in staying just inside the boundary of plausible deniability. It shows us behavior that is unusual, but not yet impossible to fold into stretched natural models. It offers us coincidences that are statistically extreme, but not impossible. It maintains a careful balance between anomaly and explanation. That balance may continue. The most likely outcome is that the object passes closest approach, looking much as it has looked already. Active, complex, and difficult, yet technically describable as a comet if one is willing to keep adjusting parameters. Papers will be written offering refined natural models. Some will focus on unusual ice mixtures. Others will focus on shape, rotation, or outgassing geometry. Many people will find those explanations satisfying. Public interest will drift. As the object fades and moves outward, it will slip from everyday attention. In that scenario, we may never know for certain whether we were looking at something truly extraordinary or at an extreme but natural outlier. That is how many cosmic mysteries end for us, not with a clear answer, but with a slowly cooling question. There is, however, another branch of possibility. The coming weeks could bring behavior that cannot be absorbed into any natural framework. A sharp change in course would be the most obvious example. Outgassing can bend a comet's path, but it does so gently and predictably. A sudden, discrete shift in direction that does not match known forces would signal active control, not passive physics. The deliberate release of secondary objects would be just as telling. Comets can fragment, but fragments share the main body's orbital dynamics and follow gravity's rules. If telescopes detect multiple objects separating cleanly from the main nucleus, with trajectories that make sense only as controlled deployments, the natural comet hypothesis would no longer be credible. Artificial electromagnetic emissions would be beyond dispute. Radio or other signals confined to narrow, unnatural bands or carrying recognizable modulation would instantly change this from an astronomical puzzle to a civilizational turning point. Even a one-time burst that we could not decode but could clearly distinguish from natural processes would be enough. The existence of someone else would switch from question to fact. These outcomes are not, in a strict sense, likely. Nature is usually subtle, not theatrical. Yet the anomalies we have already seen suggest that with 3i Atlas, we should not assume that the most ordinary outcome is guaranteed. Improbable behavior is already built into the story. So what should we do with the time that remains before closest approach? First, pay attention. That does not mean panic or obsession. It means treating this object as worthy of sustained, careful interest. The strange aspects of its behavior are not best handled by dismissing them. They are best handled by studying them. Second, press for openness. Whatever measurements are made, by civilian observatories or by national space agencies, should be shared as fully as possible. There is no good reason for a discovery of this potential importance to be handled behind closed doors. If the object is natural, open data will only strengthen that conclusion. If it is not, the broadest possible participation in analysis will be essential. Third, keep perspective. Even if future data bring us back firmly to the natural explanation, 3i Atlas is already remarkable. It is only the third known object from outside our own planetary system to pass within range of detailed study. It carries information about conditions around a different star, formed long ago and far away. Understanding it as a comet would still improve our models of how planets and smaller bodies form across the galaxy. Fourth, be ready for uncertainty to persist. It is entirely possible that December 19th will come and go without any decisive event. The data will improve, but not enough. The object will head outward on its precise path toward Jupiter, still ambiguous. Theories will remain on the table. That is not a failure. It is what happens when finite instruments meet a complex universe. Stepping back, we can gather the main threads. We have an interstellar object whose trajectory lines up with Jupiter's hill radius to a precision hard to attribute to chance. We have jets and anti-tails that stress our current understanding of cometary physics. We have a mass ejection problem that does not reconcile easily with the observed state of the nucleus. We have a perihelion period during which key maneuvers could have occurred out of view. We have a planned encounter at the edge of Jupiter's gravitational domain that looks, on paper, like an ideal deployment point. Each of these features can be addressed individually with natural explanations, some more strained than others. Taken together, they form a pattern that is difficult to ignore. The pattern does not prove intent, but it makes the question of intent reasonable to ask. What we do not have yet is certainty. No one does, despite confident statements in one direction or another. At this moment, the honest position is to admit that we are watching something whose true nature is not fully known. That statement alone is important. It reminds us that we are still early in our exploration of the universe, that gaps in our understanding remain large. If 3I Atlas turns out to be nothing more than a particularly strange comet from another system, this episode will still have been valuable. It will have pushed our models, stressed our instruments, and forced us to think more clearly about how we handle ambiguity. If, however, it is something more, if these anomalies are the fingerprints of design rather than accident, then the days around December 19th carry a different weight. They mark the first time in recorded history that we had a close view of technology not made by human hands. Either way, the passage of this object is a threshold. Before it, interstellar visitors were mostly the realm of theory and rare detection. After it, we will have lived through a concrete example, studied in real time. Our sense of the sky, of what might move through it, will not be the same. The stars have never needed us to believe anything about them. They simply are. For most of human history, we treated them as distant lights and symbols. Now we know they are suns, many with their own systems, and at least one of those other systems has sent us a visitor. For a brief period, that visitor is close enough to examine in detail. 3I Atlas approaches its closest point. 7 days remain. We watch, we record, we analyze, and we accept that some answers may come slowly, if they come at all, somewhere in the space between stars. The reality behind this object already exists, whether we understand it or not. Our task in this short window is to learn as much as we can and to be honest about what we do and do not know.